In this section, we are going to deal with the fundamental theorem of arithmetic. What fundamental theorem of arithmetic states, and states that every composite number can be expressed as the product of powers of prime in a unique way. And now we are going to, of course, the fundamental theorem of arithmetic has many applications, which we will see very soon in this section. Now we'll go to fundamental theorem of algebra, and before that I would like to give some example which leads to the statement of fundamental theorem of algebra. Now let us consider the numbers 180, 80, 99 and 250. Now we can see here 180 can be written as 180 can be written as 2 into 2 into 3 into 3 into 5. Now this can be written in this fashion because, and this is equal to 4 into 9 into 5, 4 into 9 into 5, that is going to be 180. And second one, 80 can be written as 80 can be written as now here 2 into 2 into 2 into 2 into 5. Now we can say 2 into 2 into 2 into 2 is equal to 16, into 5 is 18. And also 99 is equal to 3 into 3 into 11. Now we can say 3 into 3 is 9, 9 into 11 is 99, and 250 is equal to 2 into 5 into 5 into 5, 5 into 5 into 5 is equal to 125, into 2 is going to be 250. Now we can say these 180 and 80 and 99 and 250, they are all composite numbers. Composite numbers will mean we can write down A is said to be composite number. A can be written as B into C, where B is not equal to 1 and C is not equal to 1. Such numbers are called composite numbers. Now, therefore, above numbers are written as the product of prime numbers. Again, 180 equal to, I can write down 2 raised to 2, 2 raised to 2 into 3 raised to 2 into 5 raised to 1. And 80 is equal to 2 raised to 4 into 5 raised to 1. And 99 equal to 3 raised to 2 into 11. And 250 equal to 2 raised to 1, this is 1, into 5 raised to 3. Then what you can see here, from the above numbers, now we can see that any composite number can be written as the product of powers of primes. Now the question is it true that any composite number A not equal to 1 can be written as the product of powers of primes? Anyway, now here we have taken some particular numbers, particular composite numbers. Now, is it true that for any composite number, I mean, for any composite number, can it be written as the product of powers of 9? The answer is yes. And now the fundamental theorem of arithmetic assures us. Now we will state the fundamental theorem of arithmetic. What is that? Every composite number can be expressed as the product of primes or powers of primes, as you have seen already. And this would show some particular composite numbers. And this factorization is unique apart from the order in which the prime factors occurs. That is uniqueness. You can see here. This we have already proved that 180 equal to 180 equal to what we have done, 2 raised to 2 into 2 into 3 into 3 into 5, that which you have written as the powers of prime, that is 2 raised to 2 into 3 raised to 2 into 5 raised to 1. This also can be written as, now you can see here, 3 raised to 2 into 5 raised to 1 into 2 raised to 2. There is no change in the value of the given number, that is 180. 180 can be written is just in a different way, but in a unique way. That is the only order in which the primes occur. And the second example I can write down here, 99 equal to 3 into 3 into 11, which I can write down 3 into 11 into 3, and again I can write down 11 into 3 into 3, that is 11 into 3 raised to 2. The only order is getting changed, but the total factorization for the prime number, prime powers are the same, and therefore the expression of composite number into product of powers of prime is a unique. Now you can see who has done this one. Of course, this theorem was first recorded as the proposition 14 of the book 9 of Euclid's Elements. The proof of this theorem was found in Discussions Arithmeticae by Carl Friedrich Gauss, who lived during the 18th century, who lived during 1777 and 1855. This theorem has many applications in mathematics, such as to investigate the nature of numbers and to find the highest common factor and the least common multiple, etc. Now we can look at some applications. Example 1. Check whether there is any value of n for which 4 to n ends with 0. Now you can see the solution. Any natural number ends with 0 must be divisible by 10 or a multiple of 10, and therefore 4 is it must have 2 and 5 as factors. That is 10 equal to, because 10 is equal to 2 into 5. And therefore, now 4 raised to n can be written as 2 into 2 square, 2 raised to 2 into n, that is equal to 2 raised to 2n. And therefore 4 raised to n has only 2 as a factor, but not 5. And therefore 4 raised to n cannot end with 0. Ends with 0. And hence therefore 4 raised to n cannot ends with 0 for any n.